Welcome back to ECE 442-542. Try not to spill anything hot. But just as a reminder, homework 3 is due on tomorrow evening. I think that's when it's due on the Dropbox. Your next homework assignment number 4, which will be dealing with discrete equivalence that we're talking about today, that's due a week from tomorrow. And our next exam is 2 weeks from today. Is that right? Wow. Okay. Today what I want to do is summarize what we did last time, these numerical integration techniques, which are one way of computing discrete equivalence. We will then develop a couple of different ones of these, I think a forward and the trapezoid, in the state space format. The state space format is actually a better way to compute these discrete equivalence versus what we learned last time, which was to substitute certain expressions for z in where s is in a given transfer function. And then hopefully we will get into another form of discrete equivalence, which is the pole zero mapping. But I think you can almost derive that on your own. It's just that we have to maybe worry about what's happening at infinity, or what do we do with zeros at infinity. That's what makes the pole zero mapping technique interesting, or gives it a little bit more flavor. As a reminder, this is what we're doing. In this particular approach, it's no longer being preceded by a zero-order hold, these discrete equivalents, and we're looking at different numerical integration approaches. How do we compute this area underneath a curve, x of t? We want to go from green to blue, or we want to go from h of s to h of z. That's what we're wanting to do. And last time we illustrated where these substitutions come from. And I've tried to put it here in a sort of a tabular form. We want to create an h of z from an h of s. And we looked at 3 different ways of doing that by substituting a different z expression for all the different s's in your transfer function. If you wanted to do the forward numerical integration approach, then you replace s everywhere with the quantity z minus 1 divided by capital T. And you might, I hope with this table, you start to see a little bit of consistency between the numerical integration approaches. They all have this z minus 1 factor in the numerator, and the backward has a z, and only a z, in the denominator, and the trapezoidal, or the bilinear, is this averaging of the two. It has a z and a 1 downstairs, and it has this 2 over t in front. And so if you hear somebody talk about a bilinear transformation, that's the basic strategy. You could do some warping. We aren't going to worry about that in this class to make certain frequencies match. If we wanted to do the same discrete equivalence in the state space form, how do we go from, and now you might notice the way that I'm labeling inputs and outputs. Now my input you could think of as an air signal, and your output is maybe the input to a plant. So the output is this u of this representation. We now have x dot equal ax plus be, u is equal to cx plus de. We want to convert that into a discrete time state space form. It should be clear that this is how it would look. Not. But here's what we want to now try to understand by the end or halfway through this lecture. We have the phi, that's our system matrix in the discrete time case. We have our gamma, that's the input matrix. We have an h, and I'm calling now my output equation, I'm labeling those matrices different because they do differ. What I would like to do is illustrate, since this is a game day, we might as well just go blue and red and blue. Those are the two columns we want to derive tonight or develop. I'll let you do the green on your own. That's green for go. So you'll do that on homework number 4. But tonight, since it's a game night, we'll do the red and blue columns. Meaning, we're going to try to derive where these come from, these relationships. And what does that mean? That means if somebody gives you a continuous time system and you have it in a state space form, if you now know the capital T, which capital T is just the sample period, and you know how to pick that, now you can obtain a discrete time version, a discrete equivalent of that continuous time system in a trapezoidal form, and we kind of know what that means. In a forward numerical integration approach, that's where we simply look forward from the previous value, or the backward, which is where we look back from the present value. And the bilinear is sort of the average between that. What we want to do is feel comfortable with where do these column of formulas come from. But you now have those. You can get those when I post the notes. You don't have to hopefully write those down frantically because you might get a square root of t somewhere you don't want it. But we'll see if we can figure out what's going on. So let's look at the two different columns that I suggested we might try, which are state space numerical integration techniques. And let's just look at the forward one first. And these are actually, maybe I should say parenthetically, using these might be easier or more straightforward or more turn the crank than substituting those z expressions into h of s's in the transfer function approach. Meaning maybe you find a state space representation for a transfer function and then you apply these approaches and then you could find the discrete time transfer function if you needed a transfer function from the state space. All right, so I'm going to say that this might be more straightforward. Versus these transfer function substitutions that we worked through last time. Oh, this was the blue, so I guess maybe I should stick with the blue color for this one, the forward rule. All right, if I'm making such a big deal of colors. Let's look at the forward rule, which was the blue column in the earlier table. Where did those come from? Where did we get the phi, the gamma, the h, and the j? The system matrix, the input matrix, the output matrix, and the direct feed-through matrix. Those are what I might refer to them as. We're assuming that we have a state space representation, the input being a signal E, and the output of that system being another signal U, where the output expression formulas are consistent. So this is now our ABCD. This is typically an East Coast state space representation. The West Coast is actually an FGHJ. You really needed to know that. It may not be the same as when I learned this. So now maybe they're not so geographically connected. We're more global now, or more national in our state space representations, right? All right, here's the forward rule. If I transform this set of equations, we have dynamics, that's the x dot, and we have this output relationship, which is just a linear combination of states and inputs. If we transform this, and let's go ahead and neglect initial conditions. We're not worried about transients, so let's just not worry about initial conditions. And those might appear when we transform x dot, the derivative, if we didn't neglect them. What happens when we transform x dot? Laplace transform. We just multiply by s, don't we? We have s times capital X of s is equal to a capital X of s plus b capital E of s. And if we Laplace transform the output equation, nothing is dynamic there. That's pretty easy to transform. We simply have u of s equaling c x of s plus d E of s. And now I'm going to refer back or use or apply what we learned last time. Last time we said, oh, if we have s in our expression, we want to replace all those s's, and here we only really have one s. These are just functions of x or s. We replace s with some rule depending on whether we're doing a forward, a backward, or a trapezoidal. In the forward approach, which is what we're doing now, we learned last time that we want to replace this s, and if you've forgotten, we can just scroll back to this and say, oh, we replace our little s with z minus 1 over capital T. That's what we derived last time. If we do that, we replace s with z minus 1 over t, what that's going to allow us to do is to move into the discrete setting. Or the discrete time formulation, which means now, instead of s capital X of s, we now have z minus 1 over cap t times capital X of z. We're going into the z domain. And then everything else is the same, except we replace these s's with z's, because now we're moving into the z domain in terms of the frequency domain representation. We now, with that replacement, end up with z minus 1 over cap t times capital X of z, and it's kind of a, never mind, I won't. And there's the AB with x and e. And we can write down pretty easily the output formulation in terms of u, x, and e. Now, what we want to do is move back into the time domain from this discrete time setting. And all we have to remember is how z operates on capital X. When we operate on capital X of z with z, what's that doing in the time domain? What does little x look like? It's playing with the argument of little x, isn't it? So if we had a z to the minus 1, that's the delay. A z is an advance, isn't it? So little z times capital X is going to be little x of n plus 1. Then if we take this term, minus 1 capital X of z, that's just minus little x of n. And let's get rid of this t in the basement. Let's distribute it on the right side. So we'll multiply both sides by capital T and inverse z transform the left side and the right side, so that when we move into the time domain, I'm doing this one because this one's actually pretty straightforward, and the next one will be a little more fun. But all we're doing now is we're simply using the fact that z times capital X of z is getting mapped into the time domain into this little x of n plus 1. And x is a vector. It could be 12 tall. X could have 12 different components. Doing that, we now can say that we have x of n plus 1 minus little x of n equaling at x of n plus bt e of n. Is that clear where that came from? We're taking the top row that's still visible on the screen, that's in the frequency domain, and we're mapping that into the time domain. And we simply scaled everything by t, and that gets rid of the t in the basement. And the output equation is easy to move into the time domain. That simply says that u of n is equal to c x of n plus d little e of n. And in the discrete time, what we want is we want x at time n plus 1 equaling the right-hand side, and on the right-hand side we want something scaling x of n plus something scaling the input. And here the input is e of n. And all we have to do is really move this little x of n to the right, and if it needs to be compatible with at x of n, maybe we better put a placeholder of an identity matrix that's the same dimension as A in front of little x of n. And in doing that, we now can say that little x of n plus 1 is equal to I plus at x of n plus bt e of n, and the output equation just is copied down. And that should be the structure that we had identified in that table, meaning this is now our system matrix in the discrete time, discrete equivalent using the forward rule for numerical integration. Our system matrix phi is just whatever is scaling x at time n, and that's I plus at. And that could be a 12 by 12 matrix. I is 12 by 12, A is 12 by 12, T, that's a scalar, isn't it? That's our sample period. This is not a matrix-matrix product, that's a matrix scalar product, so there's not much to that manipulation. You just scale everything in the A matrix by capital T. What's our input matrix gamma for the discrete time system? We just look and see what's scaling the input vector, and that's just BT. The output matrix is simply C, and the direct feed-through matrix, which we were calling J in the discrete time system, is D. And so now we could write that as, oh, now I know that x of n plus 1 is this phi x of n plus gamma, whoops, this is e of n, u of n is equal to now h x of n plus j e of n. Questions on that? That's the one to warm up. That's like we're doing warm-ups. We're doing slapjacks. You know, now we're kind of warm. We can do those. But now we need to worry about maybe jogging a little. That's kind of a crawl. That wasn't much to that, right? So now we need to derive the red column. Right? Now we want to figure out where these are coming from, okay? But we're warmed up, we're okay, we're ready to go, right? So let's now step into this one. This is now the red column, and you might see this referred to as the bilinear rule for numerical integration, or the trapezoidal rule. And now what I want to do is simply start in the same place, well, partway through with what we did last time, meaning let's just go ahead, there was an s times a capital X of s, let's replace that s with that expression in z. So similar to the above substitution, now we have this 2 times capital T. We had that z minus 1, but downstairs we had a z plus 1. And that now scales capital X of z. And the right-hand side is what it was before. That's a x of z plus b e of z. That should be consistent with what we did with the forward rule. It's just that now we are using a slightly different substitution for s. And that substitution is based on this trapezoidal approximation to the area under that curve, which was really just an averaging effect. And the output equation looks like what we would expect so far. That's just u is equal to cx plus de. Now, let's push this. Well, I guess I'll do it in stages. Let's kind of clean this up and stay in the frequency domain. Let's scale everything by capital T over 2, and let's scale everything by z plus 1. Meaning, we now have on the left-hand side, we have a z times x of z minus capital X of z. But now on the right-hand side, we have several terms. We have a capital T over 2. We have an a, but then that we're scaling by a z plus 1. So we have two terms that involve an x. We have a z x of z plus a capital X of z. And we also can't forget the input piece, which is BE times that T over 2 times the Z plus 1. So in addition, I'm running out of width, so I'll just say capital T over 2, that's still on the right-hand side, B. But now we have Z E of Z plus E of Z. Everybody okay with that? Now we can take that into the time domain. I sort of did this in 2 steps. In the time domain, we have x of n plus 1 minus little x of n is equal to, and that capital T, again, that's a scalar, so I can move that right or left of capital A. If T was a matrix, I couldn't be commuting this in general. Matrices don't commute. But T is just a scalar, so I can put that AT is easier to say than TA. Maybe, or maybe this is consistent with what we had in our formula. So I now have AT, and this is now x of n plus 1 plus x of n. And I also have plus B, capital T over 2, E of n plus 1 plus E of n. And now this isn't looking so neat, is it? Okay, I have quite a few indices that have n plus 1, and I have quite a few that have n's. Before I just had the 1. That was pretty easy. I could just solve for that one piece. But now let me move all the terms on the left that or of an index n plus 1, and push all the other n's on the right-hand side of the equality. So let me now move all the little n plus 1 terms to the left-hand side of the equality. Which now leaves me with x of n plus 1 minus at over 2 x of n plus 1 minus bt over 2 e of n plus 1. And now let me put all the other x of n's and e of n's on the right-hand side. I have x of n plus at over 2x of n plus, I'm going to stretch my paper, bt over 2 e of n. So everybody, that's just algebra. Here's the fun part. Now what I want to do is actually introduce a new variable. I want to kind of clean this up, and this will actually help. Let me just call this mess on the left-hand side, let me call that a new variable, w. Kind of like we introduced an artificial variable before for the state space when we were doing our transfer function to state space representation, I think, when we were doing our block diagram manipulations. Well, this is somewhat like that, but now I'm going to actually get a little more interesting because I want to actually split my sample period into two pieces eventually, and one piece will be on the input side and one piece will be on the output side. So I want to not only say this is w, but it's scaled by the square root of capital T. So I'm going to call this mess a new variable, the square root of capital T times w of n plus 1. This is just a definition. I'm defining w of n plus 1 this way. So I'm just making that definition. If that's the case, then I can rewrite, or I can just say that the square root of t w of n plus 1 is equal to those three terms. It's equal to an x minus an at over 2x minus a bt over 2e. But those are all at the same time index, so I could just say, oh, well, w of n and x of n, x of n, and e of n have the same relationship. Let me now say then that that tells me that the square root of t times w of n is equal to little x of n minus at over 2x of n minus bt over 2 e of n. And I can clean this up a little bit. I can call this I minus at over 2 x of n minus bt over 2 e of n. And again, that's just square root of t times w of n. I'm going to need to have, well, I need to have a state space representation. So I need some vector equaling, some vector at time n plus 1 equaling some other matrix times another vector at time n. And I can do that here, wherever it is. go back here. Here's w of n plus 1. If I could rewrite this x of n in terms of w of n and e of n, I would have just w's and e's, and I wouldn't have three different variables. Meaning, this left-hand side, square root of t, w of n plus 1, is equal to some linear combination of x and e. But I now have a way of getting rid of or rewriting x in terms of w and e if I pre-multiply all three of those terms by the inverse of I minus at over 2. Is that okay? Meaning, from this equation, I can now say that little x of n is equal to I minus at over 2, and well, I can kind of squeeze it in here, I guess. Let me account for that square root of t. Inverse. Meaning if I hit both, the square root of t is a scalar. So that can slide around in and around different matrices. If I hit everything on the left by I minus at over 2 inverse, x of n becomes the square root of t I minus at over 2 inverse w of n with what else? Is that okay? So I'm really pushing that e term over and scaling everything or hitting everything on the left, and I have to keep these operations in the right order because now they're matrix operations. So x of n, little x of n, is now related to w of n, this new artificially created variable, and the input variable e, in this way, in this manner, or in this particular combination. Now what I want to do is use this x of n in those two places, in this equation. I now have the square root of t, w of n plus 1, is equal to the quantity I plus at over 2 times x of n plus bt over 2 e of n. But I have an expression for x of n. Wow, we're losing them right and left, aren't we? I told you, strap them on. We needed to wear helmets. We did the slapjacks. That was easy. Now we're... All right. So what do I have? I have the square root of t, w of n plus 1, is equal to... I just said that it's I plus at over 2. Let me just write it down for now. X of n plus that's this equation right here. This equaling the combination of those, which is I plus at over 2 x of n plus bt over 2 e of n. And now, let me use this formulation for x of n in there. Meaning, instead of writing that as little x of n, I'm going to substitute that mess on the right-hand side, which allows me to have the square root of t, w of n plus 1, equaling I plus at over 2, and I can put this square root of t wherever I want, so I'm going to slide it through. This is now I minus at over 2 inverse w of n. I plus at over 2. That's this guy. And now x of n is going to be replaced, so I now have to pick up the second term. And it's going to be pre-multiplied by the a plus I, or I plus at over 2. Meaning, I now have this plus, where was I? I plus at over 2 times I minus at over 2 inverse bt over 2 e of n. That's that term that's almost ready to go away, making up or being pre-multiplied by the I plus at over 2. Is that okay? And then I can't forget this guy. He's still there. So I have to add him in also. So I have a plus bt over 2 e of n. Did I make any more algebra mistakes or drop a minus or plus? Is that okay? Yes. What are we asking? So now did I just miss a square root of t? So I have this square root of, so x of n is square root of t, I plus minus at over 2 inverse w of n. That goes in here. Right here. So I'm using this equation right here. Square root of t, w of n plus 1, is equal to these three terms. So I'm not using this line. I'm using the one that's not really even a line. I'm using this equaling this. Maybe I should have written that down formally. How do I jump? No. Sorry. Couldn't throw that one or lose that one. So now what I want to do, because we were doing slapjacks, I have to keep going. So we have the square root of t, w of n plus 1, equaling, and this now becomes, I have to go blue because this is I plus at over 2 x of n. So did I write that down here somewhere? Yes, this is that equation that I just indicated was sort of hidden right here. That's this equaling this plus bt over 2 e of n. Is that okay? So now I have this blue box, and everywhere or the only place that I have an x of n, I now need to replace that with this highlighted yellow piece. Yes? Right here? That one, the square root of t. Whoa. That one. So that one is, I'm just saying that that's my definition of the square root of t w of n plus 1. That came from this curly brace equality, meaning the square root of t w of n plus 1 is what this curly brace is underlined. And that gives me a way to relate all of these w's, x's, and e's at the same time index. And I just said, oh, if they're true at n plus 1, they must be true at n. And that gives me this. And I used that to solve for x of n. Yes? So the square root of t is going to be placed in that definition so that I have this sample period split part on the input side and part on the output side. It will come out in the wash. Okay, so not only are we slapjacking and jumping, we're washing. But it's a game day. We're ready for it, right? Where was I? Is that helping? Yeah, we can't forget too much or I'll really get lost. We now have this blue box. This is now w of n plus 1 scaled by a square root of t. And that's now equal to several terms. But two of those terms involve e of n. And now I want to just do some matrix manipulation to clean that up. Because if you're used to seeing this I plus x, I minus x inverse, you can see something jumping out at you. But let's see where that comes from. So this is what we want to clean up. Ooh, I'm in black. Yeah, I'll do that in black. And try not to get blue here so that we're not black and blue. But what I'm wanting to do is clean up this e of n stuff. So I'm going to look at I plus at over 2, I minus at over 2 inverse, and this is just sort of have to keep track of that, plus all of that is what scales little e of n. Are we okay with that? And I want to simplify that because it's kind of ugly now. So this now I can rewrite. If I factor out the bt over 2, good thing there's not an L in there, a BLT, I'd really be hungry. So it's just a BT, and T is a scalar. Now we have I plus AT over 2, I minus AT over 2 inverse, plus I, factoring, and we have to keep track of where we're pulling these, left or right, because these are matrices. So we can only factor that out on the right. Is this okay? That should just be an algebra step. But now what we want to do, this is the way I like to see it. We can write I in all sorts of ways. But the way that I want to write it right now is a product of I minus AT over 2 and its inverse. So now I'm going to replace I, this identity matrix, with this identity matrix, a matrix times its identity, inside the square brackets. And if I do that, and at the same time factor out this common term on the right, I minus AT over 2 inverse, pardon? Is that okay? All I did was factor out or rewrite the identity matrix as a product, factor out a common matrix from those two terms inside the square brackets, and that common term was I minus AT over 2 inverse, But look at what happens inside the square brackets. Now we can relax a little, right? We've cleaned that mess up such that what's underneath, oh, and this is why I made a mistake before. Thank you for saying 2i. So I got way ahead of myself and just called that an I in my notes, so I'm going to have to correct that. And so my table up here is in error. Wow, wherever that went to. So I wondered. That should just be b times the square root of t. I'll clean that up right now because I'm going to forget about it. Like I said, I don't want to forget things, right? Meaning, wow, all the way down here I have 2 times I. Ooh, should have stayed in black, huh? Is that okay? And now I have I minus AT over 2, and this is, and those 2's cancel. So that I now have cleaned this up to where I have I minus and that is going to replace this mess that we started with. So now the only thing scaling E of n in this state space representation is going to be this result that we just derived. I minus AT over 2 inverse times BT. Is that okay? So now I'm going to go back to red and say that I now have W of n plus 1. What I want to do now is divide everything by the square root of t and get rid of that scaling factor on W of n plus 1. And it's going to get rid of that one here, but it's going to introduce a t over the square root of t, which gives me just the square root of t. So now I have, hopefully, W of n plus 1 equaling this I plus AT over 2, I minus AT over 2 inverse W of n. Is that okay? Plus what we just derived, except now we want to scale it or divide that by the square root of t, so we now have b times the square root of t E of n. Is that okay? And this should have been an inverse. Is that? And this is now our system matrix phi, and this is our input matrix gamma. And now we have something a little bit more interesting for our output equation. Now that doesn't just come straight across. U of n was equal to c times x of n, wasn't it? And x of n was this square root of t, I minus AT over 2 inverse W of n plus I minus AT over 2 inverse BT over 2 E of n plus D E of n. And if we clean that up or combine terms, we end up with U of n equaling the square root of t c, so there's the square root of t multiplying the output, and we had a square root of t multiplying the input, I minus at over 2 inverse w of n plus d plus, and this c needs to remember to get distributed into that second term in the curly bracket, c I minus at over 2 bt over 2, and this piece is now our H matrix, the output matrix, and this is our direct feed-through matrix J. So that even in this bilinear state space discrete equivalent, if somebody had a direct feed-through term that was 0, you still potentially have a direct feed-through term in this state space discrete equivalent, discrete time. And that hopefully is consistent with the phi, the gamma, the h, and the j in the table, now that we've corrected that table. Are we okay with that? Did I miss anything? So that should be what we had up here somewhere, right there. And you can see then that this square root of t is split. It's not all on the input side or all on the output side, and that was made possible by defining our w vector as the square root of t times w of n plus 1. Questions? All right, we're finished with numerical integration. Well, not, because we have an exam and you have a homework on it, but we're done in here with it. Okay, and there's going to be probably questions all over the final dealing with discrete equivalence. Don't show so much enthusiasm. Oh, you're just getting ready for the next phase. Okay, so the next phase is pole zero mapping. It's a discrete equivalent, but it's no longer numerical integration. So let's now do that. Now we want to do pole zero mapping. And again, this is another discrete equivalent technique that does not have a preceding zero-order hold involved. This is if we had a controller in the continuous time case, a C of S, and we wanted to get a C of Z. Or if somebody gave you a filter, and they said, here's an analog filter's transfer function. I want you to realize this in a computer, or in a microcontroller, or in an FPGA. Now you can do that. You can take that C of S and map it into a C of Z and put that into a bunch of difference equations. That's what we want to do now by matching poles and zeros. So the idea is very clear, I hope. All we do is we map poles in our original Laplace transform transfer function to poles of capital H of Z, and we map zeros of H of S to zeros of H of Z. And the nice thing about this, if we have stable transfer functions to begin with, since the mapping that we are going to do is all based on Z is equal to e to the st, then our stable poles that we start with will remain stable. We're just going to map them into the unit circle. because of this z equal to e to the st. They will have negative real parts, which puts them inside a radius of 1, and that gets us inside the unit circle. And in some of the numerical integration approaches, we couldn't be guaranteed of stability, could we? The forward rule didn't give us a stable h of z necessarily. Here's the approach. I'll try to do this in stages or steps. And again, this is just a discrete equivalent approach. The first thing we do is we factor the original transfer function, capital H of S, into pole and zero factors. We really just identify the poles and the zeros as factors. The second step is to map the poles of H of S to z-plane poles using z is equal to e to the st. Let me just give us an example so that we get to feeling fine with what we're doing. Suppose I had a simple transfer function. Yes, question? So now the question was, is this the same as numerical integration? And the short answer is no. We will get different h of z's for the same starting h of s in general. And with all three numerical integrations, we didn't get the same thing. And here we're going to get something slightly different using. So this is another approach. So we have discrete equivalence, and what discrete equivalence do we have? We started with zero order hold equivalence. That's where we might have a plant that's preceded by a zero order hold. Then we moved into another category where maybe we're just transforming the filter or the controller directly. And there we had numerical integration, and now we have pole zero mapping. And that's what we want to talk about now. This is now 1 over s plus a. Let's suppose that somebody says, okay, tell me about that in terms of a transfer function. And in particular, the second step was dealing with poles. Where's my pole? It's where that denominator vanishes. S equal minus a. That's, I hope, clear. So now if I have S equal minus a as my pole location in the S domain or in the Laplace domain, now I map that through the mapping. Z is equal to e to the st. Z is an advance of capital T, or Z inverse is a delay of capital T units of time. That's where that comes from. That says then that Z is equal to e to the S, which is minus a t. But in terms of a factor, I need to create a factor such that when z is equal to that, that factor vanishes. So I just subtract e to the minus at from both sides of that, and I end up with my factor that I will now have in the z domain when I had an initial factor s plus a. Now I replace that s plus a in h of s with this z minus e to the minus at in the h of z. Is that okay? And this is actually going to be downstairs as a pole, so I might want to say, oh, that's z minus e to the minus at raised to the minus 1. All right, now what we do, step 3, is we map our finite zeros. And here's where we have to distinguish between finite zeros and infinite zeros. we map the finite zeros of the S-domain transfer function, h of s, to z-plane zeros using the same strategy. We have z is equal to e to the st. And here's the fun part, or one of the fun parts. Now we have to worry about infinite zeros. Now we might have infinite zeros of our transfer function, h of s. And when do we have infinite zeros? When our denominator is of higher order than the numerator. When we have a pole zero excess. I may say, what's your pole zero excess? If you had an s squared downstairs and a constant upstairs, you would have a pole zero excess of 2. 2 poles, no zeros. Maybe your denominator was third order and you had a first order numerator. What's your pole zero excess? 3 minus 1, 2. So I may just start saying, what's your pole zero excess? Is that clear? That's how many poles do you have? 4. How many zeros do you have? 3. What's your pole zero excess? 1. 4 minus 3. All right. And that means your pole zero excess tells you how many infinite zeros you have. Infinite zeros of h of s, and here I have to put this in parentheses, are typically, and we'll give reasons when we may not want to do this, but if you're not told, then you can say, okay, I'm going to map all my infinite zeros to this factor. Infinite zeros of h of s are typically mapped to zeros at the point z equal minus 1. Meaning in our z-plane, we have this relationship between s and z that's supposed to be a semicircle without any dents, but it kind of got hit. But where is DC in the z-plane? Where did we learn DC was in the, where's DC in the s-plane? Right at the origin, isn't it? S equals 0. But now s equals 0 maps to what point in the z-plane? Z is equal to e to the st, s equals 0. This is now our DC point, isn't it? And if we now started at the origin in the s-plane and we wanted a frequency response, we would walk up the imaginary axis, wouldn't we? We would go up j omega. But where does j omega translate into in the z-plane? Now it's e to the j omega t, isn't it? And where is that? If you find the magnitude of e to the j omega t, what's the magnitude of that? It's 1, isn't it? So we're just walking along this unit circle perimeter for the frequency response. And the highest frequency that we can get to is right there at minus 1. So z equal to minus 1 is what we're associating to be our point at infinity in this discrete equivalent approach. This is our that's like infinity. So if we went to infinity and beyond, it's not very far in the z-plane, is it? It's minus 1. Whereas in the s-plane, where are you going? Infinity? You don't get there, do you? Keep going. Wherever I'm going, east. Oh, I thought you said bless you. Question? Yes. I can't hear. So now, in terms of, I'm not sure I'm quite appreciating your question, but if you think about z is equal to e to the st, and now if you say, oh, I'm looking at the frequency response, so I'm now looking at s equal to j omega, and now the furthest you can get without sort of wrapping back on yourself is right there at that point, -1. So if you look at this in terms of a complex number has a magnitude of e to the j omega t, and it has an angle of omega t, right? And what did we just agree that this magnitude was? It's just 1, isn't it? And this angle, it varies between 0 and -180 or +180, but that's as far as it goes without it start wrapping around. So this ends up being, let's say, 1 at 180 degrees, which is -1 at an extreme. So that's one way to sort of intuitively think about it. Okay? Now, what do we want? Oh, we want now for all of these infinite zeros, and that's related to the pole zero excess. How many more poles do we have than zeros? Let's say we had 2. Then for every one of those infinite zeros, we need a zero factor that when z is equal to -1, it vanishes. So z plus 1, if we substitute z equal to -1, that will vanish. And that's the factor that we will use in the numerator to represent zeros at infinity. In step 4, then, infinite zeros of h of s are typically mapped to zeros at the point z equal -1. That says then that the zero factor associated with z equal -1 is that factor z plus 1. If we return to the earlier example that we had before, which was 1 over s plus a, does that have a pole zero excess? Yes, we have one pole, no zeros. The pole zero excess is 1. That says then that we have 1, 0 at infinity. Which means that when we are starting to do the discrete equivalent using pole zero mapping, then we need a value for this. So want a 0 for this value of z, which means that that factor will give us or provide that particular property. So this is the factor in the numerator to account for that 0 at infinity, so that now we have some gain k, z plus 1 over z minus e to the minus at, and that's now our discrete equivalent using pole zero mapping and accounting for zeros at infinity. What we haven't yet done is figure out what this unknown gain is, k bar. But here, what we're saying is that each infinite zero now places a z plus 1 factor in the numerator of h of z. And now we have one more step, and that one more step is figuring out how we get rid of k bar. K bar needs to be a determined value. And that's our last step. Step 5 says adjust the gain of h of z to match, and I put that in quotes, the gain of h of s. And the reason I put that in quotes is because the gain of h of s is going to depend on what h of s represents. Is it a low-pass filter? Then we probably match gains at DC. If it's a high-pass filter, maybe we match gains at high frequencies. If it's a band pass, maybe we match the gains at a central frequency. If it's a notch, maybe we match at high or low. We decide. Is that making sense? Suppose that we now have a low-pass h of s, which we just had. Then we might have a frequency response that looks like that. And this is representing h of j omega, which is really h of s, and we might want to match the gain right there at low frequencies or at DC. Meaning we might want h of s at s equal to 0 to equal h of z when z is what? 1. And if we had it high pass, then we might have something like this, where again this is still h of j omega, but now we might want to match these transfer functions there, which now we might want h of s when s is equal to infinity to equal h of z where? At infinity, -1. So if we go back to our example, let's see if we can do this in 1 minute. All right, I'll quit laughing and then maybe we can speed up, huh? So let's say that g sub c of s is this a over s plus a, and you guys should all just be saying low-pass filter. Right? And we've already done most of this. And let's find the discrete equivalent using pole zero mapping. We do not have any finite zero, do we? And we have a pole zero excess equaling 1, which says that we now have 1 0 at infinity, and we have a pole at s equal -a. So that G sub C, where the C was supposed to be for continuous, now we have a G sub D, that's now some K. We had a 0 at infinity, that's the Z plus 1. We had a pole at minus A, that's this Z to the minus E to the minus AT. And if we find the K, K is selected. Since it's a low-pass filter to match gains at low frequencies. So that now we want G sub D of Z at DC at Z equal 1, which is K, 1 plus 1 over 1 minus E to the minus AT. That we need to equal G sub C of S when S is equal to 0, which is A over A, or 1. And now we have one equation and one unknown we can solve for K. This now tells us, by comparing those equations, that K is equal to 1 minus E to the minus AT all over 1 plus 1, or over 2. So that our transfer function, and that now gives us actually a DC gain of 1. We now have G sub D of Z is K, which is 1 minus E to the minus AT over 2 times Z plus 1 over Z minus E to the minus AT. That's now our low-pass filter using a pole zero mapping or matching discrete equivalent, and we could now put this into a difference equation to get a way of numerically low-pass filtering a waveform. And this has a DC gain of 1. If you replace this with Z's with 1, you get a 2 upstairs, and you get a 1 minus E to the minus AT that cancels the 1 minus E to the minus AT upstairs, have a DC gain of 1. We'll pick up at that point or somewhere close on Monday. Thank you for your patience with my shenanigans.